Welcome to systems with complex eigenvalues. So the theory here is, let's go ahead and consider a system y prime equals a times y, where a is an n by n constant matrix. And let's suppose that A has complex conjugate eigenvalues. Lambda equals alpha plus or minus I times beta. Then we can find complex valued eigenvectors. Corresponding to the eigenvalues. So if we pick lambda to be alpha plus I times beta, and then we can pick eigenvector, complex eigenvector psi, which is real component u plus I times imaginary component v. Then we can find complex valued solution. Y is equal to u plus iv times e to the lambda t, which is, of course, u plus iv times e to the alpha t times cosine of beta t plus I sine of beta t. If we rewrite this in real and imaginary parts, this is u times cosine of beta t, and then I squared is -1, so we would have minus v times sine of beta t for our real component, plus I times for our imaginary component. We would have v, I forgot the e to the alpha t multiplying the real component. For our imaginary component, we would have v times cosine of beta t. And then we have plus u times sine of beta t. And then that whole imaginary component also multiplying e to the alpha t. Note that when we have a complex solution broken into real and imaginary parts, the real part and the imaginary part are also themselves solutions. So the real component and imaginary components of a solution are also solutions. And so what we can do is we can pick y1 to be the real component. So y1 is u times cosine of beta t minus v times sine of beta t, all multiplying e to the alpha t. And then y2 is v times cosine of beta t plus u times sine of beta t. Again, all multiplying e to the alpha t. So let's go ahead and do this with an example. I'm just going to start off with a 2x2 system. We have y prime is equal to the 2x2 matrix 3, 4, then -5, -1, multiplying y. So the first thing we need to do is find the eigenvalues. So we have the determinant of 3 minus lambda, 4, -5, -1 minus lambda. That determinant should be equal to 0. This is 3 minus lambda times -1 minus lambda, then minus -20. Is that equal to 0? This left-hand side, we would have lambda squared. Then we have -3 lambda plus lambda is minus 2 lambda. Then we would have a -3 plus 20 is plus 17, and this is equal to 0. That left-hand side can be rewritten as lambda minus 1 squared. That would be lambda squared minus 2 lambda plus 1. And then we just have a plus 16 remaining. Is that equal to 0? Or lambda minus 1 squared plus 4 squared is equal to 0. This means that lambda is 1 plus or minus 4i. So we will go ahead and just pick lambda to be 1 plus 4i. You can also work with 1 minus 4i. That just slightly changes your when you do e to the alpha t cosine beta t plus I sine beta t, it would turn into e to the alpha t cosine beta t minus I sine beta t. It's up to you which one you want to use. They're equivalent. So in any case, we'll go ahead and work with lambda equaling 1 plus 4i. So our next step is to find the eigenvectors. So we are working with lambda as 1 plus 4i. Our matrix that we are looking at, we had 3 minus lambda. So we have 3 minus, in parentheses, 1 plus 4i. Then we had 4. Then down below we had -5 and -1 minus lambda. So we have -1 minus, in parentheses, 1 plus 4i. All of this multiplied by psi should equal the 0 vector. So we are looking at 2 minus 4i, and then 4, and -5, and then this would be -2 minus 4i. Then our augmentation is 0, 0. Working with complex values, it's not necessarily so obvious that we have a free variable. If we did our determinant correct, it should by default have a free variable. But one trick we can use is we can scale that first one so that we are, we can scale the first one to cancel out, or we can just do sort of multiple. Well, I'm going to go ahead and scale so that we can cancel out. So that first row, I'm going to do row 1 divided by 2 minus 4i. So that would give us a 1 in the first position. If we do 4 divided by 2 minus 4i, this is the same as 2 over 1 minus 2i, just dividing everything by 2. And then we can multiply the bottom by 1 plus 2i, multiply the top by 1 plus 2i, and we are looking at 2 plus 4i, all divided by 1 minus 2i times 1 plus 2i is 1 plus 4. So we are looking at 2 plus 4i divided by 5. So we have our matrix now. The first row is 1, and then 2 plus 4i all over 5, 0. For our second row, we have negative 5, negative 2 minus 4i, and 0. As you can see, if at this point we just leave row 1 alone, and if we do 5 row 1 plus row 2, we do indeed get 0, 0, 0. So this is just a way to check that we did our arithmetic correctly. We do have a free variable. We have psi1 plus 2 plus 4i over 5 times psi2 should be equal to 0. So if we pick psi2 to be negative 5, then we can pick, or then we get that psi1 would just be 2 plus 4i. So we have our vector psi is equal to 2 plus 4i and then negative 5. Personally, I just leave it like this and then multiply this by our broken out form of e to the lambda t. So next step will be to find the solutions. So I'm personally, I walk through finding the complex solution, but it's completely up to you if you want to use the formulas. So our next step is to find solutions, find real valued solutions. So I will just start with a complex solution, but you are welcome to jump to the formulas that I had written previously. So we have complex solution. Y is equal to 2 plus 4i negative 5 times our lambda was 1 plus 4i. So we have e to the 1 plus 4i t. So this becomes y is equal to 2 plus 4i negative 5 times e to the t times cosine of 4t plus I sine of 4t. And we get y would be equal to, we would have 2 cosine of 4t minus 4 sine of 4t. And then in the second component, we would have, this is a real piece. So in the second position in the real component, we would have a negative 5 cosine of 4t. Of this multiplying e to the t. Then for our imaginary component, we have plus I times. We would have 2 times sine, and we would have 4. So we have 4 cosine of 4t plus 2 sine of 4t. And then the imaginary component in the second position would just be a negative 5 sine of 4t. Again, all multiplying et. And so for our real valued solutions, we would take y1 to be the real component, 2 cosine of 4t minus 4 sine of 4t, and then negative 5 cosine of 4t for second position, all multiplying e to the t. And we would pick y2 to be 4 cosine of 4t plus 2 sine of 4t, and then negative 5 sine of 4t, all multiplying e to the t. Finally, we can go ahead and find our general solution. So y will just be equal to c1 times 2 cosine of 4t minus 4 sine of 4t, and then negative 5 cosine of 4t. That whole vector multiplying e to the t, plus c2 times 4 cosine 4t plus 2 sine of 4t, and then second component negative 5 sine of 4t. Again, all multiplying e to the t. Once again, you are welcome to use the formulas that I sort of showed you in the theory component. I often find it easiest, as I said, to just write out the complex valued solution and then break it up accordingly. But you are absolutely welcome to use the formulas that I put up. So this is how we can go about solving a 2x2 system where we have complex conjugate eigenvalues. In the next videos, we will go ahead and look at the trajectories that correspond to the 2x2 case. We will also then look at a 3x3 example.